So just like I just promised, Spencer, the first page of this is Hess's Law. So Spencer, I anticipated your question because I've done this long enough. And I also, you kind of have to trust me at this point, that Hess's Law, once you get it, once it clicks, it's just, you've got it. And so that's why I introduced it in the last one and had one on the study set. And then I want to do it again because we just have to seeing it twice. If I only did it tonight, and then there is actually in the lab. And so just seeing it multiple times, you start seeing, and you just do start getting it. So these at the top are the key, I think, to what you were just asking. So what happens to delta H when you reverse the reaction? The change signs, the sign changes. And so if it was endothermic, it becomes exo. So it's equal but opposite. So that's the idea of exo and endo. If you double the reaction, you double delta H because it's part of the stoichiometry. And when you add the reactions, you add delta H. Some of this also, some of your questions is the last thing that we're going to do tonight actually shows you how delta H's are calculated. And that may or may not, maybe for one person, help explain why this works. But yeah, Hess's Law is actually a really cool. All right. So the hardest thing I think about Hess's Law is how the question is written. You have to find what you're solving for, which is going to be the one that doesn't have a delta H with it. And so in this case, these three all have a delta H. So we're solving for the last equation. It's either going to be the last one or the first one. So like on number 4, it's the first equation that we're solving for, and we're given the other three. And so like I mentioned as we were going through the study set, I think it really helps to, one, use color or use, and make sure you can erase. So Skylar, I'm going to buy you, there's a couple students in all my classes that I want to buy you these erasable pens because it was obvious when I was grading. Your celebrations are graded, in case you didn't know that. So since I can't see any of you, you can go look if you're curious. All right, so find the piece that is unique on each of these that's in our final. This that I bracketed, this that we're solving for, we cannot change it. It is set. The other three we can change. When we change these, we change their delta H's with them. So the piece that I want from this is the C2H2. It's a visual thing again, and so I want C2H2. I only want one of them, and I want it on the product side. So you're going to have to flip the equation. And again, don't be lazy. Actually flip your equation. So the 2C2H2s, you can cut in half at the same time, but most people do something wonky then. 4 CO2s and 2 H2Os, you can leave out the states of matter when you flip it. And so when you flip it, you change the sign. It was negative. It now becomes positive. So questions with that. We're doing that because we want the C2H2 on the product side, because the equation we're solving for, that's where it is. All right, but we only want one of them. So we're going to cut these in half. So 2, 1, you don't have to write the ones. And then this would be 2.5 or 5 halves. And you want to also cut this in half, divide by 2, or say multiply by 1/2. You're going to have to show your equations since we're in this environment. So when you're going to have to show that you change things around and that things cross off. All right, so the second equation, the piece that I want is the carbons. So the carbon solid, but I want 2 of them. So I'm going to double the equation. So I'm going to multiply by 2, which means I multiply delta H by 2. All right, and then my third equation, I want the hydrogen. And we're good. It's on. So question, that arrow is key. So you need it to be on the correct side of the arrow. So I have it on the reactant side, and I want only one, because in this equation, I only want 1 mole. So I don't touch this delta H, but now I'm going to add these all up. So this now becomes a positive 2,599.2 divided by 2. You add them up, and you should get that number. So questions with that? So I'm going to pause for a minute. I want you guys to see what you can do with this one. So try it. So I'm going to go ahead and start recording. So again, find the piece that is unique. So in this equation, it's the HF. So I'm not looking at the fluorine. Why am I not looking at the fluorine, the F2?
Because it's not a product?
No.
Because they can't double it?
No. I stumped you all because it's not unique to this equation. The fluorine is here and it's here. If it's in multiple equations, you're not going to be able to touch it. It's like one of those things that it's got to work out. So you have to find the thing that is unique. I'm not looking at the hydrogen. See if we do better on this one. Why are we not looking at the hydrogen?
Because it's not unique.
In the thing? Like
It's,
the one you're trying to find, it's not used.
yeah, I think you have it, Spencer. The hydrogen's not in the equation that we're trying to solve for. So there's nothing about the hydrogen we can do. You don't want to look at the fluorine because even though it's there, the fluorine's in multiple places. So you want to find the piece that's unique. And so that's the HF. And so I do need it on the product side, right? There's our arrow, and it is on the product side, but I need 4 of them. So we're going to double everything, double, 4, and we double the delta H. All right, on the next equation, it's the CF4. So again, we're not looking at the carbon because it's not in our equation. And we're not looking at the fluorine because it was in different equations. So we're looking at the CF4. It's just like anything else we've done, like balancing equations. All of you, whenever you first learned to balance equations, whether it was like 4 years ago in high school or 10 years ago in high school, the first time it was like, what are they doing? It seems like, because it's something unique, but it's not just in chemistry, it's in anything. The first time you see, and then as you start doing it, it just starts flowing. So there's our CF4. We need 2 of them, so we're going to double and actually show the doubling. All right, and then my last equation, again, it's not the carbon, it's not the H2, it's this guy, the C2H4. And my issue is it's on the wrong side. So in the equation that I'm solving for, it's on the reactant side. So we're going to cross this off and rewrite it, C2H4. So 2 carbons and 2 hydrogen gas. And this becomes a negative. That was not well done. There we go. And so there's my C2, there's my 2 CF4s, there's my 4 HF, there's my 6 fluorines between the 2, which is what I wanted. Everything else should be crossing off. So 2 hydrogens, 2 hydrogens. So this is back to the question you'd asked me, Major. So if they're on the left of the arrow and on the right of the arrow, they will cross off. And so those 2 hydrogens cross off. I didn't do it on the one up above. We can go back and do it. The 2 carbons and the 2 carbons cross off. So that all I'm left with is the pieces that I want, the C2H4 plus the 6 fluorines. And then on the other side of the arrow, I have the 4 HFs and the 2 CF4s. And then So we have the negative 537 times 2 plus the negative 680 times 2, and then this becomes minus the 52.3, and we should be in that ballpark. On the one up above, I didn't cross out all my other pieces. We can do that. We will do that with this guy. The 2 carbons I wanted, the C2H4 I wanted from this equation, and the hydrogen I wanted. And then all the rest should cancel if you did it right. So the 2 CO2s cancel, that 1 H2O cancels, and then I have 2.5 oxygens on my product side, and here I have 2.5 oxygens on my reactant side. So all of those oxygens are going to cross off. So you're only left with those pieces. It looks like at the end a hot mess, but in the process of doing it, you know you got it because the pieces cross out that don't need to be there, and the pieces you have circled are the only thing you're left with. So Spencer, you'd asked the question, does that help a little bit?
Yeah, for sure. I literally had no idea what was going on last lecture,
Yeah.
but I think I understand.
Oh yeah, that's why I had to, yeah. That's why when we had the snow, I was like, I have to record. There's no way to do this all in one lecture because you have to kind of hear it and be like, what is she talking about? But by playing with it in the study set and the worksheet and the lab, and now you're gonna have another study set. So anybody else have questions? And please do ask. That was actually really important for Spencer to ask that question because he actually he got that answer right. All right. You guys know that mantra, no mud, no lotus? I had a mud moment today. It was a rainy day, so I gotta go stand in the mud to do my meditation. I have days like that. Don't any of you have days like that? It's a really refreshing to go stand in the mud in bare feet, especially when it's really cold. And just have a muddy moment and then realize, nope, you're all lotuses. We're all lotuses blossoming. So your innovation topics, I gave you very vague guidelines because I found when I'm vague, you guys can come up with some pretty amazing stuff. It does have to be related to chemistry, but there's like stuff we've covered this term. That gives you a lot of flexibility. So it can be something to do with heat, alternative energy, or or chemical reactions. You can go into outer space. There's some cool chemistry going on out there. We are getting into quantum mechanics, which opens up a whole possibility of things. And so on your lab Sunday, I ask for you to have an idea. I am moving the presentations. We're going to be doing them in week 10. It says week 9. I have not had a chance to fix the syllabus yet, since I'm having to reorganize 3 classes. But so let's get our innovation topics by Sunday. So if it's not going to work, I can have an email conversation. You can email me, or you can just write it on the lab and hope for the best, which is not always the best way to go. Or you can talk to me when we have a break today. But we're going to do the presentations in week 10. I haven't decided if it's going to be Tuesday or Thursday yet. I have to get through tonight first. All right, so that's the living in the moment is what I'm trying to do. So we're going to do more calorimetry. Back to the question about Hess's law. All this has to do with enthalpy. There's 3 ways to find enthalpy, and we're doing them tonight. One is Hess's law, where we have equations and we just put the equations together. One is going to be using these charts. It's going to be the last thing we do. And the other one is what we would have done in lab, which is calorimetry, what the second half of your study set was about. The difference on these problems, this is a really sophisticated calorimeter. And so they're called bomb calorimeters. I don't know why they call them bomb calorimeters, but it's much more sophisticated. They're pretty expensive. There is the thermometer, and the key is what we were doing earlier is we had the Q of the reaction. Again, I mentioned this last week, only a handful of you were here. The Q can be a capital Q or a lowercase q. I don't care. We just did, and with the lab for this weekend, it is just the reaction in the water. We ignore the calorimeter because it was made out of styrofoam. But now we have a sophisticated calorimeter. So this is where I said the reaction was equal but opposite to the solution. These calorimeters are going to be filled with water. And so this is the surroundings. The way I set this up is that the Q of the reaction is going to be equal but opposite to the Q of the water plus the Q of the calorimeter. You can do it by this first equation also, if you like to, but just to be consistent. And how this is happening is this is the system. So in chemistry, the reaction is always the system. The surroundings are, in the case of the study set that we just did, those questions 6 and 7, I think it was, the surroundings were the solution. In the bomb calorimeter, though, there's a chamber that is isolated, and the reaction happens in the chamber, and it's surrounded by water. The water is not reacting, and so the water is absorbing the heat that the reaction is given off, and the calorimeter is absorbing the heat also. And so this is where, yeah, so let's just walk through the math. So we have an extra piece is what it comes out to be, which does not happen in your lab. All right, the Q of the water is still the same, mass, change in temperature, and C of the H2O. So that piece you can do. So our mass of the water, I'm going to go ahead and keep it in kilograms. These are going to come out really large numbers, and so we're going to do them in kilojoules. Otherwise, you're going to be in the millions if you keep them in joules. So 1.20 kilograms of the water. The change in temperature, it gave us our 2 temperatures. So we have our 33.20 and our 25. So I like to write them in, and then I write what the number is above it. So 8.20 degrees Celsius. Part of that's for teaching, so you see where my numbers came from, but that also helps me if you have a mistake to be able to figure out what happened. And then just C of water. You can say W or you can say H2O. In chemistry, again, we use the number. What is the number? Yeah, it's the easiest bonus point of the night.
4.184.
Yeah, so 4.184, what are the units? I'm gonna make you work for it, Damon. He's like shuffling through his notes.
The units are, give me a second. Joules per gram degree Celsius.
Yes, joules. So it's how much heat, 4.184 joules of heat are absorbed by 1 gram of water for every 1 degree temperature change. That's what the specific heat means. So we'd punch that in. Somebody can punch that in and you would get a number. Calculator. Let's go ahead and punch it in. All right. 3 sig figs. So 41.2 kilojoules. So you can just write CH2O. Don't just write C, write CH2O, or you can write the number in with the units. So this was joules. Damon was correct. It is joules. Why is my answer in kilojoules?
This is the kilogram.
Yeah, so the K from the kilogram carries through to the kilojoules. Metric can do that. It's actually a really cool thing. All right. So next step is the Q of the calorimeter. This is our new step. So it's the same formula, but it leaves out the mass. So it's the change in temperature of the calorimeter times C of the calorimeter. And this C of the calorimeter is called the heat capacity. So this was a comment Christian made to me earlier. The C of the water and the C of the copper and of the lead and all those that we were talking about earlier, those are specific heat capacity. And in that case, if it's specific heat capacity, everybody just says specific heat, the mass of the substance does matter. For heat capacity, the mass does not matter. The size does not matter. It is just the heat capacity and the change in temperature. And the reason for that, my simple way of thinking about it, is the size of the calorimeter has already been factored in by the amount of water that is in the calorimeter. So the size of the actual calorimeter doesn't matter. The substance it was made out of is what matters, and that's the heat capacity. So the difference between them is that heat capacity doesn't factor in mass. So the units are going to be slightly different. Because the calorimeter and the water are the surroundings, their change in temperature is the same. So they have the same change in temperature. So they both are the surroundings. So 8.2 Celsius, and then it gave us in this case 837 joules per Kelvin. Again, you can change that Kelvin to degrees Celsius because we're working with temperature change, so it doesn't matter. I am going to do one more step, which is I like kilojoules. Otherwise, we were working with really big numbers. So 1,000 joules on the bottom to 1 kilojoule, and we'll punch that in. And is there questions about that? That's all there is. It's the same, but we just leave mass out. And you can see that in the unit of the heat capacity. Right. And this number is 6.86 kilojoules. Okay. So I'm breaking it into steps. I guess I did that on this one too, because I've learned over the years that for most students, doing it stepwise really helps them, especially the first time. If in the study set, I showed ones where I did it in one setup. If once you see it, you like the idea of doing it in one setup, just make sure you label your steps like I did here in the notes. So not just step one, but that you're labeling it, that you state the formula, and then you use it. So one of my pet peeves is students will like put all these formulas down, and then they have all this work all random. You state the formula as you're using the formula. So it's not like, well, when you guys are in an environment, you don't have to have everything memorized, which may not be a good thing. But the Q of the reaction is going to be equal but opposite to the Q of the water plus the Q of the calorimeter. So again, I always think of it equal and opposite. The system and surroundings have to be equal and opposite. You can also do it by setting them all up equal to 0 and then rearranging, and you get my thing here. So there is a negative now, which makes sense. So the reaction, my water did heat up. And so the reaction must have been giving off heat. It must have been exothermic. So the 41.2 and the 6.86 kilojoules. All right, that would be that. And then what are we going to do to go to delta H? Somebody's got to know. I mentioned it earlier. So delta H is enthalpy, and the difference between Q is heat or heat flow. The difference is enthalpy is always going to be per how much reacted, so per mole. So all we're doing is taking that step and dividing by moles. So what moles are reacting? In this case, it was the octane. So again, the water does not react. The water is the surroundings. So it's going to be the moles of the C8H18. So if you like, you could combine these steps or you can have them separate. So what was that number? I'll give you, yeah. Our denominator is going to be, so some students like to figure this step out separate and then put the two pieces together. So we have the 1 gram that was given at the very beginning of the problem. And then we just have to figure out our grams per mole. And I'm going to pause us. You can go ahead and punch and crunch numbers and see if you get it. And then I'll give you a chance. What are we solving for? Oh, you can at least do step 2 down here. You can ponder step 1 if you like. I'm going to pause us for a moment. Hopefully you're all back. All right, so up here, when we add these two together, you should get negative 48.1 because we are limited to the 10th place. You can keep it in your calculator. And then on the bottom, you can figure out what this number is, or you can punch it all in. And we're limited to 3 sig figs. So the 0 is a placeholder. It is negative. Combustions are always exothermic. In case you didn't know that, that's why your car works. That's why our body works. Combustions are exothermic. And they're always pretty large number. The more carbons you have, the larger it's going to be. So that's why for our car, it's C8, it's octane. And then trucks use diesel because they're even larger. All right, so on this one, lots of information. You can underline all of that. We're looking for the mass of the water. So we are given the heat of combustion, and that is delta H. How do I know that's a delta H number? It doesn't say, hey, this is delta H equals this. It just says the heat of combustion is this. What is the key in there that tells me this is delta H and not Q? Go ahead.
I think I'm wrong. Is it because of kilojoules and moles?
It's because of the moles.
Okay.
Yes, it is because of the moles. So if it says per moles, that is not a Q. And for us to work with this up here, they all had to be Qs. To be able to make the water and the calorimeter opposite of the reaction, we have to change the reaction to just kilojoules or just joules. Again, you have to go along with me, so you have to do kilojoules tonight. So we have to get rid of the moles to make it, excuse me, a Q. Yeah, so what do we have? We have 1 gram of octane. Did I do octane again? Oh, good. That makes it easy. So 1 mole of octane is 114 grams. And wow, 1.00 grams. These are like from Joyce 25 years ago, because I'm using 1 gram. I don't like use much more interesting numbers, but we get a number there. So questions with that is the key. So from the previous lecture, whatever the mess was in there, I'm really impressed by myself because there's a full moon tomorrow night and full moons mess me up. And so I'm doing really good. So does anybody know what moon it is? Let's make me Google it. The full moons always have special names. It's a really gentle full moon as opposed to the last one, but it's why I had a mud moment today. Yeah, but the big key here today is at least get this idea, the difference between a Q and a delta H. Simply, I mean, there is, you can Google enthalpy versus heat, but it is per how much is involved. So per the reaction, the moles.
There's no moon.
It is a snow moon. He Googles faster than all the rest of you. All right, so negative, keep that negative there. 48.2 kilojoules. And so the other thing I keep mentioning, show your units, state your formula. This one, of course, is a factor label step. So we don't have a formula, but we state that's delta H. This is now a Q because it's just the Q of the reaction. The sign is really important, and same when you're working with temperature changes. All right, the Q of the calorimeter, our equation, our formula is just change in temperature times C of the calorimeter. So our change in temperature is the 35.2 minus the 26. And then the heat capacity, oh, it's the same number. We're still using the same problem. I wonder if it's going to have the same mass of water. Nope, doesn't. All right. I'm going to change it to kilojoules. You want all of them to be the same unit. I think it's easier to work in kilojoules. Having watched people with lots of zeros for years get lost in the zeros. And this is what, 9.2? 0. So 7.7. 0 kilojoules. All right. So for the Q of the water, we could actually, there's going to be a step 4. The Q of the water, we have to do this, that the Q, you can set it up like I did here, or you can go back to this piece, that 0 equals, just to be different, equals Q of the reaction plus Q of the water plus Q of the calorimeter. So, sorry. If you add them all up, you have 0. So we're solving for Q of the water. So we move the other 2 to the other side. So we're going to have negative the Q of the reaction plus the Q of the calorimeter will equal the Q of the water. So basically, whatever one you're solving for, the other 2 are on the other side. This is where the sign is crucial. This is this negative is outside the parentheses, and then we have a negative 48.2 kilojoules inside, plus a positive 7.7 kilojoules. And right, so that's going to be like 40. .5. Yeah. Questions with that? So Max was here earlier and asked me something with the worksheet. So there's a question on the worksheet where you're solving for temperature. I also be careful with temperature changes because they can be positive or negative, and that makes all the difference. I recommend if I ever ask you to solve for temperature, you actually solve for the temperature change and then go to the temperature. So solve for the delta T. All right, so there is a step 4, and step 4, I'm pretty sure you can all do, which is, and again, you could set it all up as one formula, that the Q of the water equals the mass of the water, change in temperature of the water, and C of the water. So this is our Q, 40.5 kilojoules. What are we solving for? The mass of the water. So we will divide by the change in temperature, which is our 9.2. And C of water is, they all say 4.184. In chemistry, it's 4.184. When you take physics, it will be 4.186. So it is not an exact number. So it's probably, some of it's a rounding thing, and I think it's how it is calculated. And so I think in chemistry, it was done experimentally, because chemists like to do experiments, and probably in physics, and I'm not remembering when I sat through Fausto's physics. He's awesome. He's amazing. And when we did calorimetry in there, because they're not looking at it as far as chemical reactions, I think I remember thinking, oh, that's why it's slightly different, but just go with it. All right, and do we get my number? So 1.05, and it's kilograms. Back to the question I'd asked earlier. Since this is in kilojoules, your mass is in kilograms. And so don't let that inspire you going, that's really cool that we can do that with metric units. All right, questions with calorimetry. And you can absolutely break it into steps. I think on the lab, I give you a nice half page like that. And yeah. All right. Yeah, there's the lab. Do I give you lots of room? Oh, we don't do that problem on the lab. All right. Last page. So there is in the week 8 folder, there is a chart. You do not need to print the chart. I should have mentioned that earlier. If you printed the chart, great. Just know it's there. We all have to use the same chart. And I mentioned this chart last week. There are delta H's, which are enthalpy. There are S, which stands for, does anybody know what the S stands for?
Disorder.
It stands for disorder. Thank you. Yeah, it's entropy. It's disorder. And does anybody know what delta G stands for? That's delta G. This guy gets. What were you gonna say, Christian?
I said free energy.
Oh, free energy. Yeah, the guy gives free energy. So he gets to be on a stamp all the time whenever they do famous American scientists. Most people cannot understand his math, but in Chem 223, we come back and we use the whole chart. For right now, we're just going to use the first column. And these charts is just somebody did a lot of chemical reactions and figured out a lot of numbers for us. I tried to, what did I do with my notes? There we go. I tried to simplify this. And I just simplified the chart down to this. Partly because we all have to have the same states of matter. And so what the chart is delta HF. It is, and delta H is enthalpy, or sometimes they say heat, but it's not a perfect synonym. And the F is for formation. And what it stands for is the formation. You're going to form 1 mole of the compound. I talked about this last week because it's bizarre, from its elements. So the compound is the product. This is not the same as heat of reaction. That's what we're going to be calculating. The delta H of formation, this is the chart. And it's just like this esoteric thing. So we're going to do it for calcium carbonate. So calcium is a +2 and carbonate is CO3 is a -2. So that's our formula for calcium carbonate. Calcium carbonate is clamshell, so it is a solid. Carbonates are solid. So the elements are not CO2. It's not calcium plus CO2. CO2 is not an element. It's calcium plus carbon plus oxygen. Oxygen is a diatomic, so diatomics are diatomics. States of matter are crucial. So in this chart, you will find, like for bromine here, you have bromine as Br, you have Br2 liquid, Br2 gas. The one that is how the element is in its standard state is the Br2 liquid. Elements in their standard state, so the elements in their standard state, I don't know who came up with these words, that they are state of matter dependent. So oxygen is a gas, calcium is a solid. And does anybody remember what we say? Carbon you can write solid, but to get
Graphite.
the full, it is graphite. Yeah, so there is the chart I posted only shows diamond and graphite, but there's several other forms of carbon now. Does anybody know all the forms of carbon? There we go. You can email me. That's a good question. There's like 5 different forms of carbon. There's always somebody who's shy and they're like, I don't want to speak up in class. I had a gal last term, and anytime I asked, there were 2 of them. But all of you, even if your name's on the board, you can Google it, and then you can write to me about all the different forms of carbon. Not when it's in a compound, but now we have to balance this. This has to stay as a 1. So we have 1 calcium, we have 1 carbon, and for the oxygen, we write 3/2. So we do use fractions for balancing equations in this with the chart. All right, so that's what the chart means. This would be what that equation would look like. It's kind of bizarre. What we're going to do is write real chemical equations, and then I'll show you how to use the chart. We might get done early. All right, so we're going to do combustion. So what is combustion? So C3H8. Combustion is, go ahead, write your equation, balance your equation. If you're still warm because we're doing thermodynamics tonight. This is my Sherpa hat made out of yak wool. That's Damon can be jealous. I might have an extra one. I don't have the pink one. Pink one is mine. We went to Nepal. It was in the summer. It was like 105 degrees. It was the monsoon. And then we flew up into the Himalayas, and I was so cold. And I was so happy to find a hat. It wasn't this one. It was a Rasta hat. It was awesome. I gave that one away to a student. Yeah, we have several yak wool hats, Sherpa hats, made by real Sherpas. All right, so you're gonna end up with CO2 and H2O. So the one on the celebration on the exam was you had to get CO2, H2O, and NO2. The balancing was really big because of that nitrogen there. But yeah, so. All right, balancing, we need 3 carbons, 4 H2Os, and that gives us 5 oxygens. What's wrong with my equation?
States of matter.
Doesn't have to.
Yeah, gotta have states of matter. So now I did mention when you guys were writing states of matter, you could do everything as gas. For this, we have to all have the same states of matter. And so we're going to go with what's in my little chart here. And that's actually why I made the little chart. So we're going to make the C3H8. We're going to make propane a liquid. Here we go. Put a lot of pressure. Oxygen's a gas. CO2 is a gas. And H2O could be a liquid or gas. So if the equation's given, we're going to go with that. Here, we're going to go with the liquid. If I don't give you the states of matter, you can use whatever you want, and then I'll have figured it out. All right, so we're going to find delta H of reaction using the numbers. So the numbers in the chart are these delta H formation, which is these esoteric equations. And the formula that you got to keep stating is most students condense it down to just products minus reactants. So it's always final minus initial, but those little fancy things mean the sum. So it's a sigma sum of the delta H of formations of the products minus the sum of the delta H of formation of reactants. So again, the F means the chart formation, since we're using those numbers. Reaction means for the whole reaction. This is the one, back to the question Spencer had asked me a long time ago tonight, like a whole hour ago. This is when we write at the end of the reaction, like in the homework, when we did the Hess's law, those are delta H's of reaction. We write them at the end of there. All right, so we're solving for that here. Our products. This is to get full credit. You have to label fully. I don't want a bunch of numbers. You guys don't get multiple choice with me. You can pick a different teacher next term. They do all multiple choice. Have fun with that. So 3 moles of CO2. You miss one question, you use 5. Like you don't get part credit. I love multiple choice. And you know why teachers love it? They don't have to grade. They don't have to spend like 6 hours sitting on staring at a computer. Like, wrong, wrong, wrong. You didn't answer it, -5, right? You've all done that. And then you're like, but I really did. See, I circled D, but I wrote B. I don't know why I did that. Sorry. Love multiple choice. Totally like I'd be the worst concept in teaching of all time, right? All right. So you're going to label. You have 3 moles of CO2. I'm starting with the products times its number, which was from our little chart. And the units from the chart are over here, kilojoules per mole. And then plus your 4 moles of H2O times this number. The chart usually uses 6 sig figs. I start condensing down to 3 eventually. Okay, so those are my reactants. I'm sorry, those are my products. And then I'm going to subtract my 1 mole. I'm going to run out of room. So start way over or write smaller than your teacher does. 1 mole of this guy times its number. And then I ignore the oxygen. You can ignore the oxygen. The oxygen was needed to get our balanced equation. But why can I ignore the oxygen?
Because in its state it's 0, so you're just adding nothing.
Yeah, so elements are not compounds. So there's nothing needed to form it. Elements are 0 delta H of formation. Again, that is only when they're in their standard state. So the bromine, like from the first page of the chart. Again, you don't have to print the chart. It's there. If you already did, that's great. But it's a 0 for as a liquid, but as a gas or as a monatomic, it does have numbers. All right. And then you would put all those numbers in. Did I not give you answers? Oh, I did. Great. I don't have to put them all in. And we should get around negative 2,220. Combustions are always large numbers. And my answer makes sense because it's exothermic. And I made that comment earlier. Combustions are exothermic. So we're going to do the thing again. Going to pause for 5 minutes. Go ahead and write your combustion of C6H6. Balance your equation and then work out. See if you can get there. Practice showing your work beautifully. If you're really good, you can try the one down here. Down here, this is algebra. We're solving for, I give you the delta H of the reaction, and you're solving for the SiO2. This is your X, your unknown. So I'm going to pause. You guys can try that. You can take a break for 5 minutes. Is there something with mushrooms or algae and global warming, or algae being used for energy? I forget now what it was. There's the tides being used for energy. That's like a big research thing at Oregon State. So much potential. There's new ways to do solar power, like with changing the solar panels so that they work much better. All right. So combustion. And our state is a liquid plus oxygen, which is a gas. We can go to CO2 gas and H2O liquid. And oh dear, does it say? All right, so I didn't mention this. Probably all of you didn't get my answer. This is per mole of C6H6. So when I do this 6 CO2s and 3 H2Os, I have to keep this as a 1. So we're going to have to use a fraction to balance. So if your answer came out double this, that's why. So we have 12, 15, so it's going to be 7.5. All right, so you would state your formula. So our delta H of our reaction is our products minus our reactants. and, or you can be really nice. It's fun writing the sigma sign. So we have 6 moles of CO2. You guys got the idea, right? Times the negative 393.5. Writing all your units, make it look really pretty. Plus 3 moles of H2O. So if you didn't get my answer, or you just took a break, I was getting lots of good ideas there. Am I recording? All right, so label. Your teacher has a pet peeve about this. The other teachers all talk about how Sherpa will mark you wrong if you don't label it clearly. So label. Yeah. All right. So I did want to mention that actually with grades. So I did post your celebrations today. Got it done. We do have the presentations is 50 points. It's a paper, like a 3-page paper again. I don't even know what I wrote for that. So 3 to 5 pages, and then your presentation like we did before. Find a topic that's going to make you really enthusiastic to talk about it. And you do have to find more than one reference on it. So ideally 3 sources. It could be an interview with somebody for one of the sources, but that is 50 points plus 15 points, so 65 points of participating, meaning that you listen to your classmates and write comments and ask questions. And so that gives everybody a big boost before our 3rd celebration. Also, get your work in. Just get it in on time, like the lab this weekend, just do it. It's just number crunching. Right, so that's this week 8 lab. The peer review will be week 9, and there'll be the quantum. We get into quantum mechanics next. Those of you had Chem 104 or 151, half of quantum mechanics is math. That's going to be new stuff. But half of it is electron orbitals, the 1s2, 2s2, the arrows. So we could get back to something you know. All right, and then minus, we do want to label 1 mole is C6H6. And that was 49. Now back to the sig fig thing. Technically, my answer should have gone to a place value, but it didn't. So, oh well, I lost the point. There's a bonus you can do with the lab. There's a bonus on every worksheet. Just stay after and come to office hours or come early. Somebody gets around my answer. I'm assuming we're good. All right. And then this one. So again, state our formulas. Delta H of the reaction is equal to our products minus the reactants, right? And be careful of the sign. So this is endothermic. Finally, an endothermic. 54.8 kilojoules. Now, technically, this is a question students will often ask me. Delta H's, when we write them at the end of a reaction, we usually leave out the per mole because it's per mole based on the stoichiometry of the reaction. So we just leave that bit out, but it's kind of implied. All right, we're going to do our products first. So 1 mole of SiF4, and there's that number. Negative 1614.9. I'm pretty sure at some point I start rounding them more. Plus the 2 moles of H2O. And yeah, just let me know when I go off the camera with my writing. I'm really good at that. Right, H2O is liquid, and that's this number. So the biggest thing I find with these is more punching in your calculator. So that's all my products. And then we're going to go minus, nothing gets left out on this one. So 1 mole of the SiO2, that's going to be my X, because that's what we're solving for. Notice it's in the minus though, with the 4 moles of the HF, and the HF was whatever, negative 332.6 kilojoules per mole. There's also some cool stuff you can do with plastics. I'm trying to think of ideas for you all. I don't want to limit your thoughts though. Oxidation reduction, there's some cool stuff. I'm thinking there can be some really cool stuff there with medicine, because I know some of you are going towards medical fields. Yeah. So if you find an idea, send me an email, and you can even send me, if you have a web page link to it, you can send that so I can look at it and say, yeah, that will work. But remember, it is chemistry, so we want to have some kind of chemical relationship. And so you're solving for X. When you rearrange, you are not solving for negative X, you're solving for X. So you will get negative 910-ish, 0.9 kilojoules. This is kilojoules per mole because it is a delta H formation, because we technically do divide by that 1 mole. All right, questions for the good of the order?
If you wanted to put the last one, sorry, if you wanted to put the last one in the, like in order, if you want to rearrange it.
So yeah, this is all adding and subtracting. Thank you. I knew there was a question. I couldn't figure out what it was. So when you're using the chart and you're solving for X, there's no division happening here. So what I would do is add up take this, right, figure out this. And because that's a negative, when you figure out this number, we can figure it out because you're not the only one. Some of you have that solve function, but whatever that all is, you're going to move all this over by subtracting all of that. And that's going to equal this negative. Then you have to change the negative, right? Just cancel the negative, change the sign of the other side. And then you're going to have to subtract this number. Does that make sense?
Yeah, so we subtracted the number that comes out of the 54.8 subtracted from the number that comes out of these two.
This whole thing.
All of that we subtracted from the very last one on the right.
Yeah.
Okay, cool.
Well, exactly opposite of how you said it, but
Okay.
Okay.
Oh,
I
there you
think it's an
go. Thank
English. I think it's an English thing because people in my house say it like that too. It's how we use our prepositions in the English language is actually the part that's weird. So yes, but for people who are listening to this explanation, it may have confused them. All right. Was there any other questions? So yeah, it is. It's not dividing here. It's adding and subtracting. So you're moving by adding and subtracting. So be careful of that. That is different from what we did like on the first page of your study set. So that's actually a really important question. All right, I am going to stop.